record on this computer. Okay. All right. So someone asked about matrix exponentiation and posted a video on, or a link to Geeks for Geeks page on matrix exponentiation. And honestly, looking at the page, I don't quite understand what the algorithm, like I understand the gist of what they're trying to do. And that's essentially what I'm hoping to explain. But the algorithm that they actually have is just bizarre. And it's not very clear about what's going on. So really the algorithm that they're talking about is about a fast exponentiation algorithm, not about a fast matrix exponentiation algorithm. And the reason for that is because, well, a fast matrix exponentiation algorithm has to sort of be a generalized fast exponentiation algorithm, because the idea there is that actually multiplying two matrices is expensive. And so you want to reduce the amount of times that you're doing that multiplication. So the sort of standard way that you would go about doing multiplication or exponentiation. So let's say you're trying to do, change something real quick. Okay. So let's say you're trying to do a to the power of b. You're doing a to the power of b. And for the sake of this, I'm assuming b is just an integer, because a positive integer, because doing anything else just starts to get really complicated, and also just doesn't make sense for matrices. You can't just take negative powers and assume it'll work. So the very, very basic approach, the first algorithm you might write is something like this. And I'll use a Python syntax here. For I in range b, res times equals a. And that would be the very first algorithm you might think, right? Just multiply a by itself b times. The problem is that, well, this is O of b, and it's actually slightly more complicated than O of b. Technically, it's O of b log a, sort of. The reason for that is because, I mean, at least in Python, if you're just multiplying numbers and just getting bigger and bigger and bigger numbers, these numbers are eventually going to get large enough that it's going to have to use an algorithm to do the multiplication itself, which is roughly O of natural log of a. Though, like, if you're just doing basic multiplication, then, and the numbers are small enough, like they could fit in an integer or something, then it's just going to be O of b, which seems like it's good, right? It seems linear. But the thing is that whenever you're dealing with algorithms that are on numbers, what is generally considered to be the base value is the natural log of the number. So if you're describing this algorithm here, if it's O of b, then it's actually O of e to the ln b. So this is actually an exponential algorithm. And the reason that you consider the natural log is, or the log, and really it's not the natural log, but it's the log base 2. And the reason for that is because the log base 2 of b is the number of bits, binary bits required to represent that number. And most algorithms on computers are going to deal in the number of bits that they have to manipulate, not the actual size of the number. So this algorithm here is O of 2 to the power of log base 2 of b, or O of b, which is obviously bad. Exponential algorithms are bad. So can we actually come up with an O of log base 2 of b algorithm? So now to go off on a seemingly unrelated tangent. So let's say we take the number, what would be a good number here? 13. Now, I'm going to sort of do a process here on the number 13 to get it into a very, very specific form. So here, 13 is odd, so I'm going to break it apart into the even counterpart plus 1. Well, now this is even. This is 2 times a number, so I can say, well, this is 2 times 6 plus 1. Well, I'm going to take the 6 here. It's even, so I don't have to break it apart into the plus 1. So I'll just go ahead and do 2 times the number. So 2 times 3 plus, and I'll just write it as 0 for that sake. Then, well, 3 here, that's not a 2 or a 1, so I'll break it apart again. So it's odd, so I'll have to break it apart into 2 plus 1. And then finally, I'm basically done here. I can just put a 1 there. And now everything is either adding 1, adding 0, or multiplying by 2. Now, that was possible for 13. Should this, in theory, be possible for any number? Does anyone have any idea?
Should be, I think.
Do you think you could explain why?
I mean, like...
Let me write this out just a little bit more.
Like if it's odd, subtract 1, otherwise divide by 2. Like that'll get you any integer, at least. You should be able to get down to that form.
Yeah. Can anybody tell me what the significance of these numbers is?
Is it some weird bit thing? Is it going to be like the carry or something?
That's literally 13 in binary.
Oh, no way.
So this is just another way to phrase the binary decomposition. But the thing that you can think about this is that all you're doing here is you're multiplying a value by 2, which is equivalent to squaring. So if you think about this as in the exponent, right? So if I was taking something to the 13th power, it's the same thing as doing a to the this power, which looks bizarre. But all it is you can reformulate this as the exponent, right? Because you can use exponent rules. The addition of 2 exponents becomes the multiplication of 2 things. And doubling an exponent is equivalent to squaring something. So what this ends up doing is we have, I'll actually do it down here. So let's say we're doing a to the 13. So doing a to the 13, assuming that multiplying, like you can do the multiplication in any order. Sometimes you can't do that, but for matrices you can. You can associate in any way that you want, and the result is always going to be. You can't like change the order necessarily, but so yeah. So we get that a to the 13th is equal to a to the 2 times 2 times 2 times 1 plus 1, 0 plus 1. Okay, so now I've got an addition, so I can break this apart into 2. I can just break this apart into a times this stuff times just a on its own. A times 2 just then times a. I guess that 1 goes away. 1. So now you can use the exponent rule for multiplication. So if you have a to the power of the product of 2 things, you can bring one of them as the exponent of the other. So this is actually equal to a to the 2 times 2 times 1 plus 1 plus 0 squared times a. And then I can keep this process going. So now, well, here I have the plus 0, so that doesn't, that's just, that I can just drop that, and then I can bring the 2 as an exponent again. So then I get a to the 2 times 1, 2 times 1 plus 1 squared times a, which is in turn equal to a squared times a squared times a. Now, why, what in God's name is the point of doing this? Okay, well, if you're doing the naive algorithm for a to the 13th, you're going to do, if you're using this algorithm here, if you start by 1 and then consecutively take powers, you're going to do 13 multiplications. How many multiplications does this do? Okay, so we have 1 for the squared, 2 for this multiplication here. Then in this parentheses here with the squared, that's 3, 4, 5. So there's just literally less multiplications. And it's done in such a way that you're going to keep track of a really, really big value. And so rather than just multiplying your really, really big value by a just once at a time, we'll use squaring as a mechanism to sort of jump really far ahead in the line. And the reason that we can use squaring in this manner is because you can decompose the exponent in binary.
Nice.
This looks complicated, but it's actually really, really easy to write recursively. So we can just say that a to the power of b is equal to a to the power of b. I'll use that for integer division. A to the power of b integer divided by 2 squared times a to the power of b mod 2. So we can recursively compute this, and this is either a or just the identity, right? This is either a or 1, because this exponent is either going to be 0 or 1. So basically, we can just say, okay, well, recursively, we'll figure out what a to the power of half of b is. We can then multiply that by itself to get a to the power of b if it's even, or a to the power of b minus 1 if b is odd. And then we just have to multiply by an extra a to do that. This is actually equivalent to constructing the binary numbers in this way. So this is 13 in binary. So if we sort of look bottom up, what we'll end up doing is we'll start with one copy of a. When we square a, that doubles the exponent. And doubling in binary is the same thing as shifting it over by 1 to the left and putting a 0 back in its place. So what we're doing there is we're saying, okay, get the previous one, then square it, which is the same thing as shifting the exponent over by 1. And then possibly we need to put a 1 in this position. In this case, we do to construct this properly. So then we'll shift this over again. We'll get 1, 1, 0. So now, because we want a 0 in this position, we don't actually want to add, we don't want to do that extra multiplication by a again, because we want a 0 in this position. And then we shift it over again. We would get 0, 0. But then we can say, oh, well, we can just multiply by a again to get that we've multiplied a by itself 13 times. And this sort of pattern right here is exactly this pattern here. It's start with 1, multiply it by 2, shift it over by 1, then add a 1 in the position you missed. That's what, when you multiply by a, that's what happens. Then we'll square that. That's the same thing as shifting. But when we squared this time, we didn't add a 1 in the original position because we want it to be a 0 eventually. Then we square it again, so that shifts it over again, and then put a 1 in that position. And that is exactly the same process as this here. Okay. So let me pull out some code now. Show what's going on here. I don't believe you can see my screen. I think I'm only sharing.
Yeah, we can't see it.
I'll just go in here and share my desktop. That'll be easier. Okay. So I've implemented it in 2 ways. So I've implemented the recursion way. First of all, up here. So I have my base and my exponent. And here, notice, I'm not doing anything with matrices. I'm just doing this with an arbitrary base and an arbitrary exponent. But what I'm doing is I'm actually allowing the ability to pass a special multiplication function into it. So that way, if I want to multiply matrices, I can pass in a function that says, hey, here's how you multiply the matrices. By default, however, it just uses like literally the times operator. That's what operator.mul does there. So this will work for matrices. If you pass in the right multiplication function, it'll work for literally whatever you want. It works for just normal numbers and whatever. There's nothing special at all about this being for matrices. I'll get to that later. So yeah, all we do is if the exponent is 1, then I'll just return the base value. Otherwise, I will recursively call POW with exactly half, the integer half of the exponent, then multiply that by itself. And if I need to, I'll just multiply by the base an extra time if I need to. And that's the whole algorithm. This is recursive, however, which isn't too much of a problem because the recursion depth here is going to be the log of the number of the exponent. And so if your exponent is a 32-bit number, this will at most recurse 32 times, which isn't a big deal. However, recursion is slower than not using recursion. Iteration is just faster than recursion. So a non-recursive solution would be slightly better. And so what I've done here is implemented the exact same algorithm, except now I'm reading the underlying binary of the exponent, because really that's all I need to do. So here I basically, this stuff at the beginning. So, well, if the exponent is 1, I just return the base because that's just easier to handle. Otherwise, I make a scanner here. So if you look at the binary number, so let's say it's 13, I'll write it as 8 bits. So what the scanner here is going to do is it's going to just start at 1, and then it's going to shift over, and then it's going to shift over, and then it's going to shift over until it's bigger than 13, and then it'll just shift back 1. So essentially all this is going to do is it's just going to find the leftmost one in the binary number. Because that's the reason that it's easy to implement recursively is because it essentially is doing this. It says, okay, well, I'm going to take 13, my matrix to the power of this, then I'll square that, and then possibly multiply by an extra copy of the base. So if I want to do this non-recursively, I have to start from the left side of the number, which is a little weird, but then it's essentially just the same process. So then I just start at the base. I'm sort of shifting the scanner over to the right one by one. So that way I'm essentially going to check each bit from left to right. And then I just do the same thing. I just multiply the current result by itself. So that squares it. And then if the specific bit that I'm on is a 1, then I multiply by the base an extra time. And I have this mod here just so that I can keep numbers small in some examples. But you can leave that out. Like if you don't actually want to do like mod anything, you don't need that there. But these two are exactly the same algorithm.
So is that and you have on line 27? That's a bitwise and?
Yes.
Okay.
So the scanner basically is, it's a 1 in a very specific position, and then I'm using bitwise and to check to see if there's a 1 in the exponent in that exact same place.
You said recursion is slower than iteration. Is that true in all cases?
Yes.
Like it's just like more expensive to call the recursive stack?
Because of the way that recursion works, or function calls work, actually. And especially with recursive functions, like if I was doing this in C++ specifically, a lot of function calls can get optimized out. Like it will just inline functions because that's just way faster. The problem is, in order to do a function call, here's all you have to do. So if you're familiar with the architecture terms, this will make sense. Otherwise, it doesn't. Like it's not that big of a deal. All you need to know is recursion is slow. So in order to perform a recursive call, the first thing that you do is every single variable that you have stored in a register has to be put back into memory.
Okay. Yeah.
Because calling a function essentially gives the function entire control over the CPU. 2, it has to, it has to store the current location in the code that is running so that the function can return back to that place.
Okay. Yep.
It then has to call the function. If the function is known ahead of time, then that's not too expensive. But if the CPU can essentially look ahead and say, oh, I'm going to need to jump here in 3 lines, so I'm actually going to like prepare that jump ahead of time. But if like you're doing some like polymorphic thing where the function is unknown, that's even slower because it basically can't know the function up until the point it needs to call it. But anyways, it does that. So then inside of the function, the first thing that it's going to do is it's going to allocate all of the local variables in that function on the stack. If you're just iterating, none of that happens. Because if you're iterating, it doesn't have to store all of the local variables into memory. Like it can just keep them in registers and just keep working with them in the register. It doesn't have to store its current location anywhere because it doesn't care. It's just going to execute the code. It doesn't have to actually jump to some random place in the code that's maybe very, very far away. That can also just cause some time lag. So in general, a function call is always expensive.
That is also really interesting to know.
There's a max recursion depth, so if you're doing it iteratively, you just don't have to worry about that. So like if you're doing something that scales up a ton, you can't do it recursively because it will hit a limit. It's either, I think
But
it's
yeah, and the reason that there is a recursion depth is because when you call a function, what it does is it allocates local variables on the stack. It also puts the return value on the stack. Well, then the next function does the same thing. And then if it recursively calls, it's just going to constantly be building up the stack, and it's just going to eat up your memory.
Right.
And the compiler or whatever has built-in stuff to basically just prevent you from consuming all of the memory. You can like disable limits, recursion limits, or increase them. Like in Python, there's a like a library that you can call a function in that just increases the recursion depth. And that's basically just telling the OS, like, okay, yes, I know I'm going really deep recursively, but it's fine that it's using up this memory. Like the alternative is just manually building a stack and manually handling that, which is just a lot of work. So
interesting. Huh.
And I say function calls are expensive, and they're relatively expensive. To something like an addition or a loop, they're expensive. But really, like they're pretty cheap in comparison to a lot of things. So
interesting.
It really just depends on what you're doing. If you're like looking for performance, function calls are something that you actually have to pay attention to.
That's good enough.
So
thank you.
So I've got these two here. I guess I'll just quit out of this one. So here I've got just some timings for different POW functions. So I've got, here is just the normal iterative POW function. Here is the built-in POW function. Here's the recursive POW function, and here's the looping based POW function. So we'll just start with num here, and all I'm doing is this number to the power of itself. So it's gonna be a massive number. And I'm also doing a modulus by a specific number so that the numbers don't get too large. These are all integers, so Python's actually able to do this, but the larger the numbers get, the longer the multiplications take, and eventually just like ends up taking forever to do anything. So just modding by a number keeps everything small, but it's still completely unpredictable. Like you can't guess ahead of time what the value would be. So it just helps keep things out. So if I go ahead and run this, as POW tests. So you can see already the iterative POW is relatively slow. The recursive POW is slightly slower than the looping POW, but the looping POW function that I wrote is it's slightly over half as slow as the built-in POW function, which I would guess would be written in C. It could be written in Python, but if I had to guess, it's probably using a similar algorithm. So yeah, it's definitely fast, and that was a relatively small number. If I start to go up to larger numbers, and we can see it also is the same value for all of them, so it is working. So if I do this, now the iterative POW, it's starting to get significantly slower. The custom ones that I implemented are also getting a little bit slower in relation. You can see here that the recursive is slightly slower. It's not that much slower than the larger one. So if I'll just go up to the next level here. Is this big enough for people? Let me see. I should be able to increase the size here a little bit.
Just hitting Control+ usually works too.
So yeah, so now let's see. So now the recursion one is getting to be significantly, like an order of magnitude almost slower than the normal POW. And now I got to this number, and if you've seen on line 35 here, I have a check to run the iterative POW. And that's because this takes, I think, 7-ish seconds to do the iterative POW, whereas the other two are still pretty fast. Like the looping POW is about half as slow as the built-in POW, and the recursive one's starting to get quite a bit slower. So yeah, works very well. So and this again, like the way that I implemented it and just the algorithm in general, that works on literally any object that can be multiplied. And this is just an even larger number. So, and yeah, it just works. So to get to matrices specifically, just to show some of this stuff. So I have just some basic utility functions for dealing with matrices. So I've got a transpose function, an invert function. This is only for 2x2 matrices. And I'll get to why. Then you have dot products, matrix, taking a matrix and multiplying it by a vector on the right, matrix by matrix multiplication. And then these are just functions that allow me to create functions that allow me to mod matrices for the same reason as this here. I'm going to be taking really large powers of matrices, and if I just let the values go out to infinity, it just gets too big to do anything reasonable. So I've got that. And I guess I'll just go to the matrix stuff now. So now for this, I will comment out, let's see, this call here for now. So here I've got, and I'm going to be doing Fibonacci because it turns out that you can use a matrix to compute Fibonacci. And I'll show that. But here I've just got a standard Fibonacci implementation that doesn't use an array or anything. It just adds the numbers together and swaps, adds, swaps, adds, swaps, adds, swaps, and then returns the correct value at the end. Here I've got what you might think is the only option if you're dealing with matrices. And this is just basically you take your vector, multiply it by the matrix, then take the result of that, multiply it by the next matrix, and you just do it one at a time. So this, this is essentially equivalent to squaring, like taking the power of the matrix just by doing the iterative approach, which is slow. But if you're not thinking about it, it's really, really easy to, well, actually, I should get back to here so I can explain this a little bit more. So the idea here is you have a matrix A, and you have a vector V, and you're trying to compute A to the n times V. There's a couple of reasons for this. One, here specifically is a way to represent Fibonacci, or at least one iteration of Fibonacci. So if I start with this matrix here, and I start off with the vector 1, 1, and I multiply this, well, you get 1, 2. And the reason for that is what happens is if you sort of imagine you're actually doing 0 times 1, or if I just put AB here, and I draw out what that is, AB, well, this ends up being B, A plus B. Right, so this encodes one iteration of Fibonacci. And so if you multiply this by this and you just keep doing that over and over again, you're just going to get Fibonacci. And this is actually a relatively efficient implementation of Fibonacci. Even though it is doing iteration one at a time, it actually is going to be like faster than filling out a whole array or something like that, or at least it'll use less memory. Another reason that you might want to do this, and this is getting a little bit into math, but this is actually kind of an interesting topic. So let's say, and I'm dealing with 2x2 matrices just because I didn't feel like implementing some of this stuff for larger matrices, though the general matrix multiplication algorithm I have would work. So imagine you have a graph with just two nodes here, and they're kind of pointing to each other and to themselves. And what you can do here is give a probability to each of these edges. So let's say I have a 0.9 probability and a 0.1 probability. And over here, let's say from this node, I have a 0.5 probability of going back to itself and a 0.5 probability of going to the other one. And notice here, the probability is going out of a single node added to 1. So this is what's known as a Markov chain, if you've ever heard of those. And all you can do here is you can say, okay, well, I'm going to start here. And then I'm going to do one time step. And one time says, so, okay, roll a dice, like a 10-sided dice. If you roll a 1, stay here. If you roll anything else, go here. And that'll be one step in the Markov chain. So after one iteration, if you started here, after one iteration, there is now a 10% chance that you're here and a 90% chance that you're here, right? It's pretty basic. But what happens if you start doing more iterations? What if you say, okay, I start here, and then I'm going to do that process 100,000 times? What's the probability that I end up here, and what's the probability that I end up here? Now that gets significantly more complicated. And well, this is a graph. You can encode a graph as a matrix. So what I can do here is I can say, okay, well, this will be node 0 and node 1. We'll say this is, or I guess I should call them something different. Let's say A and B. So this is A and this is B. So for A, and this is A and B. So this is going to be from and to. So if I'm at A, I'll say, well, going to A, I have a 10% chance, and going to B, I have a 90% chance. And then from B, I have a 50% chance of going to A and a 50% chance of going to B. And then I can take, let's say, if I'm starting in A, then I'll start off with this. And this basically says there's a 100% chance that I'm in A and a 0% chance in a B. That's how you would describe that, the fact that you started A. And then if I do a single multiplication here, well, this will just end up being 0.1, 0.9, exactly those probabilities. So this will describe that there's a 10% chance I'm in A and a 90% chance I'm in B. And what you can do is you can then take powers of this matrix to say that you're doing multiple steps. So this is a really useful, like for statistical simulations, this is a really useful thing to be able to take powers of exponents and then multiply that by take a power of a matrix and then multiply that by some vector. And yeah, naively, what you might think is you just do that one matrix vector multiplication and you just keep multiplying the resulting vector by the matrix to get whatever you have. So, but that isn't going to be efficient, but that's this basic algorithm. On the other hand, I'm just going to use my POW loop function to exponentiate the matrix itself and then multiply it by the, the vector. So I've got the power here for the matrix and n, and then I just multiply it by the vector. And I'll get to this one later. So first I have Fibonacci here. So this is the same exact Fibonacci matrix and the same exact initial vector. And so now if I want to get the 10th Fibonacci number, I think I might be off by a number because I had to do fastfib n+1 here for it to work. But if I'll go ahead and save this. And now I want so now we can see that all three of them get 89, at least for the first coordinate. And they do so in a varying amount of times. Am I doing modulo here? Yeah. So here I'm doing modulus just because otherwise this thing blows up to infinity too fast. So let's just go for the 10,000 Fibonacci number. So, well, if you look at that first function, the fast fib, that took 0.002 seconds. The first mat powvec, that's just doing the iterative matrix multiplication. But the third one is doing the fast power, and it's actually faster than the naive Fibonacci implementation because it actually runs in log n time, not in n time, like the fast Fibonacci function. So using this matrix exponentiation trick here, you can actually get faster than like typical Fibonacci implementations. I can even go to crazier values. What is that? 100? No, that's a million. So the millionth Fibonacci number, that took not too long to figure out. It took 1/10,000th or almost 2/10,000ths of a second to compute it with the matrix exponentiation. But with the normal fast fib, it took 14 hundredths of a second. And it took 1.4 seconds for the matrix. And the reason is that the fast fib and that first matrix power function are essentially the same time complexity. They're just doing one of these iterations one at a time constantly. It's just the matrix one's just doing so much more work because it's doing a matrix multiplication. Then going, and we can do something similar now with, and again here I had the modulus going on, so these are relatively small, but that's just so that these numbers don't blow up to infinity. So let's see, what was the matrix? It was, I think, 0.1, 0.9. So here I've got the same exact matrix for that Markov chain. And I want to know, well, what happens after a million steps, or let's say 10 steps? What's the probability of being in A or in B? So if I do this here, I'm going to remove the modulus. So here, well, you get it's a 35.721% chance to be in A and 64.27% chance to be in B after 10 steps. And you can see with the first one, they're roughly the same speed at this point, because that's not really doing a whole lot of iterations to figure out what happens in 10 steps. But one of the things that you can do with the Markov chain is consider the limit as you do infinite iterations. So basically, like if you just left this Markov chain running for an infinite amount of time and then it randomly stopped it, what's the probability that you would be in one of the two positions? So instead of looking at a specific number of steps, this just says, okay, well, kind of think of this as like a random thing. Oh, well, you can see this is actually the limit bound that I have for the slow one, but it'll spit it out. And yeah, it took 11 seconds to do it iteratively, and almost 3 10,000ths of a second to do it with the fast exponentiation. So it's definitely faster, that's for sure, and very, very useful. So it also, and yeah, this is actually a really, really useful way. This is a really useful use of it, doing these Markov chains, because they have some statistical uses.
So just so like the one that's like crazy fast, the PowVec2, that's using the loop you coded in the first example for the bit. What? Okay.
The Pow loop.
That's crazy.
And yeah, I have I'm passing special functions. So here I'm passing my custom matrix multiplication function in as the way that it does the multiplications. And then I also have a modulus in there just because otherwise it would just get massive.
Interesting. So do languages default to doing multiplication, like exponents, this way, or do they do?
I believe so, yes. However, built-in POW functions typically only work on integers. So they're probably doing something even more specialized than that. There's probably faster algorithms.
Interesting.
However, the POW function I wrote there works on literally anything, any object that can be multiplied by itself through whatever means. So it works on matrices. It can work on like weird objects if you want to do it on those. Just because, again, like the link that Vincent had posted, it's literally just talking about a fast exponentiation algorithm. The matrix is just there because it's useful for matrices. Okay, so I have one last thing coming out. So for those of you, so the reason that this algorithm is nice is it works on anything that can be multiplied by itself. However, it makes a really, really naive assumption about what it means for a number to be able to be multiplied by itself. It just assumes that there's nothing special you can do in the background to make things faster. And the thing is with matrices is that there is actually a faster way to exponentiate for certain matrices, not all. If you took linear algebra and you learn about eigenvalues, it's actually they're actually very, very useful for decomposing matrices in a specific way. So let me pull this back up here. So what ends up happening? So let's say I have a matrix A here, and somehow I find two matrices, one named P, one named D, and then I take the inverse of P. So I'm assuming here that P is an invertible matrix, and I can sort of represent A by P times D times P inverse. So now A to the N, I can write that as P D P inverse, P D P inverse, and so on, right? Well, if you look here in the middle, I'm doing P inverse times P, which cancels itself out. That just becomes the identity, and then the identity times anything is just the identity. So this actually is equal to P D to the N P inverse. Now, why is this useful? If you can represent D as a very specific type of matrix. And the reason I called it D here is because typically when you do this sort of decomposition, the goal is to have a diagonal matrix here. If you have a matrix that is 0 everywhere except exactly right down the diagonal, this is very easy to exponentiate. This to the n is just a to the n, b to the n. Because those zeros everywhere else just end up not doing anything. And so you can exponentiate a diagonal matrix extremely fast, as quickly as you could just exponentiate n individual numbers, rather than having to do these complex matrix multiplications. So I wrote some code that basically can take A and automatically create these matrices for 2x2 matrices. You can do same sort of algorithm, the same sort of stuff for 3x3, 4x4, and 4x4 matrices, but you cannot do it for 5x5 matrices. Like mathematicians have proven that it's impossible to do for 5x5s because there is no quintic formula. There is a quadratic formula, there's a cubic formula, and if you want to go out, there is a quartic formula for 4th degree polynomials, but there is no formula to find all of the roots of a degree 5 polynomial. If you want to do that, you'd have to go to some numerical methods. So I'm not going to get too much into this because it probably would get very boring. But it's essentially just if you did any sort of eigenvalue, eigenvector decomposition problems in linear algebra, it's essentially just going through that process here. And so I can take any matrix here, pass it into here. And in one specific case, if like the two diagonals are already 0, it's already diagonal, so I don't really have to do anything. Otherwise, I get the 2 eigenvalues. Then based off of the 2 eigenvalues, and so yeah, with the 2 eigenvalues, you can create the diagonal matrix. So this is one value in one corner and one value in the other, and the other 2 are 0. Then I can get 2 eigenvectors from the matrix corresponding to those eigenvalues. And here I'm assuming the 2 eigenvalues are different. I'd have to write slightly different code if they happen to be the same. I just didn't feel like handling that case. And then the P is just essentially placing those eigenvectors in the columns of P, and then P inverse I just compute as the inverse. And it's guaranteed to be invertible because the eigenvectors are going to be linearly independent. So it's pretty much just doing how you would do this on paper, but using a computer. So if I open the POW tests now and I see, so now I have a third function here. And what this does is I take the matrix, I get the decomposition of the matrix. Sometimes the decomposition doesn't work. Sometimes this just literally is not possible for certain matrices, and you'd literally have to do something like this. Then I get the 2 entries in the diagonal matrix, and I exponentiate them individually and create that matrix. So I can compute d to the power of n just by doing POW on just single numbers, which is going to be very, very fast. And here you can see I'm actually using my own POW function just to sort of make it a more fair comparison in speed. And then, yeah, so then what I do is I take P, I multiply it by d to the power of n, multiply that by P inverse, and then I just multiply that by my vector, and I'll get the result. So how does this compare? So first of all, this is going to be inaccurate. Why? Well, if I pull up this here, so you can see in the evals thing, I'm doing subtraction and multiplication, which is all fine, but then I do a square root. So the moment I do the square root here, everything starts becoming floats or doubles, I think, in the background. And at that point, you add an accuracy to everything you're doing. There is going to be floating point errors because floats don't have infinite precision. So this isn't completely accurate. However, if you could mathematically compute all of these and actually store them, this would be 100% accurate. It's on a computer. There's finite precision, so you can't just store as many decimal places as you want and just expect it to work. So let me go back to the Fibonacci example here. And I want to go back to these. Okay. So I'll start back at a small number. So we'll go with 1. So 1 is just a single matrix multiplication. Doesn't seem like it would do a lot. But at the very least, this just at least shows you that this decomposition does in fact work. And if I do this here, we'll see that, well, the first Fibonacci is 1, and then the vectors are all going to be 1, 2, 1, 2, 1, 2. So it did 1 power correctly. But yeah, and just something just to point it out, there is 3 matrix multiplications that are all done in this one. Otherwise, the pals are just done on individual elements. So this thing does literally a finite number of matrix multiplications every single time. So let's go up to 2. And we can see here, oh, 2, 3, it's still accurate now. Let's go up to 3. So now you start seeing there's a couple of decimal points. So now it's 2.99999, close enough. But it's going to stop being accurate fairly quickly, at least for Fibonacci. And the reason for that is because it's growing. And because it's growing, the values are getting bigger and bigger. Inaccuracies are going to become more and more obvious. So let's jump up to like 10. So we're getting almost 89 and almost 144. So it's still working. And now let's take a look at comparing the speeds. So now if you look here, the eigenvalue one, you can see the values are very, very far off. And the reason for that is because it's doing a modulo, and the error is always going to be in the lower terms anyways. So the error is always going to appear here. But if I wasn't doing modulo, you'd see that the numbers would actually be relatively accurate. It's just otherwise they would get too big. But you can see here that now this eigenvalue decomposition trick is faster than all of the previous implementations, because now it's doing an efficient POW on individual numbers. It's not even exponentiating a matrix. It's just doing it on the 2 values of a specific diagonal matrix. And I can go up even higher. I think that's is this the max value? Yeah, this is the max value for I have for one of the matrix multiplications so that it doesn't take too long. So the fast fib took 1.5 seconds. That's the one that you'd hope to be pretty much or as fast, but as you saw already, using the more efficient POW on a matrix is even faster than that. And the slow matrix one that just does it iteratively, that's obviously the slowest. Then the fast POW, that one's did it in 2/10,000th of a second, but the eigenvalue one was even faster than that, which is pretty interesting. So here, another thing I can do here, just to show you that it actually is fairly accurate, I'll convert the other ones to use floats, just by doing that there, even this one here, and then I'll remove the mod. So now the problem is that the floats end up going off to inf, but it'll at least show you that there is a good bit of accuracy still in this. If I do like to the power of 1,000, you'll see that they're all pretty close for the first couple of digits. But obviously, it's to the power of times 10 to the power of 208. So these are just massive numbers because Fibonacci grows really quickly. And then, yeah, so now the Markov chain one's more interesting because the values stay bounded. They always stay between 0 and 1. So the eigenvalue one actually becomes extremely viable for this. And keep in mind, this isn't any sort of approximation. This is exact. This is, if the floats were higher precision, this would be exactly correct. So if I do now for, let's say 100, oh, I'm going to change these back. So now with the same Markov chain, we can see that after some iterations, they're all roughly the same speed. The eigenvalue one is still faster, even just at 10, which is somewhat surprising. But now going off to, let's say, 100,000 iterations. So after 100,000 steps, where do these values end up being? And again, the speed is very, very fast. And you can see that now all three of the answers are exactly the same up to like, I think 12 decimal places, which I believe is the precision of a double. So these are essentially all within standard floating point error, roughly. And the third one is actually incredibly fast. So these work very well for things where the matrix transformation stays bounded. And I can go up even higher. And something very bizarre that I saw happen, we'll see if it happens again. So this should be slow because the first one is, you know, just doing the standard multiply the vector by the matrix and then just keep doing that one at a time. Yeah, so here it's still very accurate and just still the fastest. If I go even higher, so now it'll drop the first one. So these are still good. I was using a different example. So this is kind of crazy. Like this is a 2-node Markov chain, and I'm simulating, what is that? 10 billion iterations in a fraction of a second because I'm able to actually compute the value directly. I don't have to do any weird thing. I can just say there's just, and this is just because of the math behind it. You don't actually have to simulate like a random coin toss or anything like that. This is identical, but you can see the eigenvalue one just does not. Oh, well, that's a little bit slower now, but it's still 6 times faster than the other one. I'm not seeing here. Let me change the matrix to something different. So I don't know, we'll say 0.9.1 and then 7.3. So now there's like they have a each of the nodes has a relatively high probability of transitioning to the other one, or no, they have a relatively high probability of staying where they are. 0.9 in one and 0.7 in the other. And it was something a little more drastic like this that was, oh, well, you can see here, it looks like these values converge to 75% and 25%. Interesting. I'm trying to, I think I had just some more extreme numbers or something like that, but I don't know. I'm probably not going to see it, but the first one in one of the other matrices that I was using, it actually, the first function eventually stopped working. Eventually the values just all went to 0 for some reason, and the eigenvalue one didn't. I am not entirely sure why that was the case. It's definitely, I think I can undo actually just everything here. No, that was the same function. Oh, well. Why did that slow down? Oh, wait, that's why. Let's see if I can get this to happen. Nope. Okay. Well, it doesn't seem to be happening. But yeah, the one that where it does where it exponentiates the matrix and then multiplies by the vector, that one literally stopped working as a simulation. My guess is that when you're doing the matrix multiplication, like the errors were compounding extremely, whereas with just taking pow on a single number, it's a lot more well behaved because it's a single number. It's not like a multiple numbers interacting with each other. That's what I would have to guess. So this actually just ends up being more stable for that reason. That it's just exponentiating a single number by a really, really, really large number. And I guess it can just be more accurate because of that. But yeah, that's pretty much what I got for today.
The amount of math tricks I mean, I guess they're not tricks because it's like just straight math, but the